So I'm going to run through some of this with you, and then some of it I'm going to ask you to do on your own in groups. And then I'd like for you to do some practice problems before you move on to the next unit, just to make sure everybody's got this nailed down. So first of all, you've got a chemical reaction there written out in words. Butane burns completely in oxygen to yield carbon dioxide and water. So what you're going to want to do is, first of all, by this point, you ought to be able to write down the chemical reaction from these words. You know all of these molecules, and balance it. So butane is a hydrocarbon with 4 carbons, C4H10, burns completely in oxygen to yield carbon dioxide and water. Okay, that's your combustion reaction that we've looked at a lot this semester. Okay, so the first thing is you have to write down each molecule correctly. Then after you do that, you need to go back and balance it. So in this case, you have 4 carbons here and only 1 carbon here. So we're going to put a coefficient 4 in front of the carbon dioxide. And then next, always go to your hydrogen. There are 10 hydrogens on the left-hand side, and there are 2 on the right-hand side. So just put a coefficient 5. 5 times 2 is 10. So now the carbon is balanced and the hydrogen is balanced. The last thing to balance is the oxygen. We, of course, only have 2 oxygen atoms on this side. And on this side, we have 8 plus 5 is 13. So, and then we have 2 over here, so you have an odd number on this side and an even number on this side. So there's a trick where you can say, okay, I have 13 halves oxygen, so 13 halves times O2 is just equal to 13. So that is just a little balancing trick. And then I always want to clear my fractions when I'm balancing, so then I can multiply both sides of this equation by 2. And then ultimately the balanced equation is 2 butane plus 13 oxygen equals 8 carbon dioxide plus 10 water. Okay, so now I have a balanced chemical reaction. You guys should all be able to do that by now. All right, so for reaction stoichiometry, what it is it's a way of knowing the balanced chemical equation, predicting how many moles or how many grams of product or reactant you get given a certain amount, because this balanced chemical reaction tells me the whole number ratios of molecule to molecule to molecule. For example, in order to combust completely all 2 moles, and I can read this as individuals or moles, and I'm going to read it as moles because it makes more sense. 2 moles of butane will combust completely with 13 moles of oxygen. So they will combust in a ratio of 2 to 13 or 13 to 2. And every time I completely combust 2 moles of butane, assuming I have at least 13 moles of oxygen, I'm going to produce 8 moles of carbon dioxide. So that's a 2 to 8 molar ratio. And the same goes for water. Every time I combust 2 moles of butane, I'm going to end up with 10 moles of water. All right, so there's a lot that can be read out of these chemical reactions. For example, how many moles of oxygen are required to react completely with 5.6 moles of butane? So what if instead of having 2 moles of butane, I had 5.6 moles of butane? So what you do is you just, because the chemical reaction is balanced, it's an equation, you can actually use the equation as a conversion factor to knowing the amount of one reactant or product, predict the amount of the other reactant or product that is going to be needed or produced. So what I mean is just start with what's given. You're given 5.6 moles of butane. And then what's wanted is how many moles of oxygen are needed to combust completely 5.6 moles of butane. All right, so then we need a conversion path to get from one thing to the other and to get from moles of butane to moles of oxygen. And so if I just have this reaction, I can use the reaction to get my conversion path. And the conversion path is going to be from moles of butane, and I'm going to be converting to moles of oxygen. And so the conversion factor, that's what I meant to say before, the conversion factor can be read from the balanced chemical reaction, and the conversion factor is the whole number ratio of moles to moles. Every time I react 2 moles of butane, I'm going to react 13 moles of oxygen. So you can actually say 2 moles, I'm going to do this over at the side here, 2 moles of butane equals 13 moles of oxygen. It's a little equality. It's like a conversion factor. Every time I react 2 moles of butane in this balanced chemical reaction, I'm going to react 13 moles of oxygen. So I can say 2 moles of butane equals 13 moles of oxygen. So if I want to make that into a conversion factor, then, and I know I want to convert from butane to oxygen, then I would divide both sides of the equation by butane. 2 moles of butane divided by 2 moles of butane. And I've just created a unit factor. 2 moles of butane divided by 2 moles of butane is the same as 1. So 13 moles of oxygen per 2 moles of butane is now a conversion factor that I can use in this conversion problem. So 13 moles of oxygen divided by 2 moles of butane is now a conversion factor or a unit factor because it comes from the equation, and the ratios are fixed in that chemical equation. All right, and so then just to work the problem, you just start with what's given, 5.6 moles of butane times the conversion factor, 13 moles of oxygen are consumed every time I combust 2 moles of butane. That's what that means. The moles of butane is going to cancel, and we'll be left with the desired units, which is moles of oxygen. And so when you do the math there, you get 36 moles of oxygen. So that's how we use our balanced chemical equation to predict, given a certain quantity of one reactant, how much of the other reactant am I going to need. In this case, it was we were given a certain amount of butane, and we're going to predict how much oxygen we're going to need to react all that away, and it's 36 moles.